The Cambrian explosion was obviously a very interesting time. We're starting to get some very good constraints on what's happening biologically over this time. But I want to look more about the environment of it. So it's not just a biological revolution, it's an ecological revolution as well. So one of the most important Phanerozoic environmental proxies is the stable oxygen isotope ratio, which is a ratio between something that comes out normally much better than that, ratio between heavy oxygen, oxygen 18, and lighter oxygen, oxygen 16. And this comes from a variety of sources, but mostly from calcareous brachiopods and from phosphatic conodonts, which are obviously only used for the Paleozoic data. And the oxygen isotope data is locked up in the biominerals of these fossils. Now, oxygen isotopes are useful for constraining a few things, including temperature of the water that the animals are living in, salinity, which can also be used as a proxy for ice volume, so how much global ice there is, and also potentially how much for sea water volume as well. But this is further complicated, unfortunately, by things called vital effects, which is how the oxygen isotopes get from the seawater through the animal and into the shell, and what is actually recorded in the shell isn't just a simple environmental signature, it's also got something to do with the biological processes behind shell growth or skeletal growth. So we've got a pretty good Phanerozoic record, and a reasonable Paleozoic record as well, where calcareous brachiopods fall down, where there's some gaps in the record, particularly in the lower Paleozoic. Conodont data take over, and broadly speaking, get fairly similar trends between the two, though there are some important differences. Where this falls down is the Cambrian period, which has effectively no reliable stable oxygen isotope data at the moment. This is partly due to the fact that euconodonts, the clade with diagenetically robust elements, haven't yet evolved, or they only appear in the uppermost Cambrian. And calcareous brachiopods are generally found to be fairly poorly preserved over this time. Calcite alters much more easily than phosphate in diagenetic conditions, so calcareous brachiopods just haven't really been shown to be reliable and robust to diagenesis, so we get a distorted signal. So if we're looking at the Cambrian, we need some alternative. So just to pin down why exactly this is important, like I said earlier, it's the biological revolution, but also the ecological revolution, and going back to these wonderful creatures again. And we still don't have much quantitative data for environmental conditions, so including global temperatures and temperature gradients. Paleogeographies are still, they're getting better, they're getting better constrained, but there are still some big uncertainties there. And the stability of the climate over this time is still not particularly well known. There are lots of qualitative descriptions. It's generally a warm time, a warm environment with very little or no ice, but that's about where it stops, and we do need some alternative sources of quantitative paleoenvironmental data, which is where these things come in. So small shelly fossils, they are exactly what they sound like. They're small and they're shelly, and they're fossils of some of the earliest biomineralizing animals that we know of. They include various cap-shaped things, a lot of which are interpreted as mollusks, but can be interpreted as a few other bits and pieces as well. We have some sponge spicules, various phosphatic tubes, which are quite useful. Odd things called tomotiids, which we're starting to get a better idea of what they are, but what the individual animals look like is still a little bit anyone's guess. And we have lots and lots of micro brachiopods as well. So these are lingulid phosphatic brachiopods, rather than the calcareous brachiopods that are used elsewhere in the Paleozoic. So some of these taxa are primarily phosphatic, some are primarily calcareous, and some, like sponges, primarily siliceous. But where we have phosphatic taxa, and they're still preserved in phosphate, there's a chance that that phosphate retains an original environmental signal, and we can use this to get our environmental constraints. So how do you get from these little things, small shelly fossils, down to an oxygen isotope ratio which you can then reliably use to infer paleo-environment, paleo-climate? Well, we have to check that effectively there's been no remineralization and no change in the isotope ratio in the skeletons of these things over geological time, which in this case is about 500 million years, and a lot can happen. So, I'm going to present to you the preliminary results of the protocol that we've been putting together to assess the preservation state of these phosphatic microfossils. First of all, we look at microstructures, and just to make sure there's no crude overall diagenetic alteration. We then look at the ultrastructure to make sure that there's been no finer scale remineralization. I look at chemistry to check for other diagenetic signals. Chemical alteration is generally an easier thing to pick up, so we're looking into that as well. And a bit of future work is to look at the crystallography to make sure we haven't got pseudomorphing minerals that won't be picked up in the first two of these tests. I should say the reason for these various stages is because each one gets progressively slightly more time-consuming and progressively more expensive. So if you can knock a few things out of the early stages, it makes it a lot easier when it gets to the later stages. So, to take the microstructure of a phosphatic brachiopod, we have a modern analogue for these. They're extant lingula and Glotidia, two lingulid brachiopod species still alive today. They have skeletons, or shells rather, composed of alternating compact layers of phosphate made of small phosphatic spherules with organic layers in between, or organic rich layers in between, and so that's what we'd expect to see in fractured specimens, and it is exactly what we do see. We find compact layers of compact laminae of phosphate separated by more porous laminae, which would have in life been very organic rich. To take another specimen at the microstructure scale, a thing called Rhombocomiculum. It's a weird spine-shaped microfossil, thought to be primarily phosphatic, and it's composed of a net-like cross-section. So take a cross-section across here, it looks like sort of net-like or mesh-like appearance to it, and when you look at it in that orientation, you find effectively pillars of phosphate separating these net-like holes, or these more porous areas. And when we take a look and zoom in on a fractured specimen, we find we do have prismatic and net-like appearance going through, and to take a polished, that's very bright, to take a polished section through this, we find that we have got the dense rod-like structures running through, and what's much less clear on this image than should be is the more porous net-like fabric running through it, and which you can find in here. So within this specimen we have well-preserved microstructure and ultrastructure, or apologies, well-preserved microstructure at this scale, in between fractures which are filled with iron oxide. So alteration has occurred to this specimen, you can see it at this scale, but an area in here in between may still be suitable for suitably well preserved. So to take a look at the ultrastructure of this specimen, we find that we have to take that previous image and zooming right in on it, we have small spherules of phosphate in these more compact rod-like areas of phosphate. And the net-like fabric, in this case, shows slightly coarser but still sub-micron grains of phosphate, biological apatite, which would have been in between the organic infilling of the net-like structure during life. So to now jump on to the chemistry stage. Biological apatite is primarily made of calcium phosphate. It's also got a component of fluorine in it, and may or may not have bits of magnesium and sodium coming from seawater. It's found from modern lingulid brachiopod compositions. So we find, as expected, that phosphate and calcium make up the most part of these, in particular the compact laminae of the brachiopod, which you can see is sectioned here. And there is also fluorine present, though relatively enriched in the more porous areas with respect to the denser, compact laminae. Now, iron is not something we expect in large abundance in lingular brachiopods, but in this case we find that we do have quite a bit of it surrounding this specimen and indeed penetrating into the specimen. However, the compact laminae are these black areas in the middle, and these black areas suggest that actually they haven't been remineralized. So whilst we have got iron oxide, in this case, infilling some of the more porous laminae, making this specimen not necessarily suitable for a bulk analysis, if you can isolate compact laminae, which are seemingly well preserved and not affected by this secondary chemistry, then bits of the sample may well be suitably well preserved. And we see a very similar pattern with Rhombocomiculum. So this is a cross-section cut through perpendicular to the axis of growth of this sample. And we see here that the central canal which is infilled with sediment, has iron and silica in it, but all of the iron and silica alteration is restricted to the fractures that we see here as well, and is only there in relatively low abundance. So this specimen, away from the fractured surfaces and removing the core, is, again, probably at this level well preserved. So from the crystallography aspect, this is a bit of further work which is sort of in development at the moment, and it's something that's been brought to the attention of the paleontology community by Maggie Cusack. I hope I'm pronouncing her name correctly. And it's a technique called electron backscatter diffraction, and we're working on this at the moment, but it basically gives crystallographic orientations, and you can find that crystallographic orientation should be preserved within a single layer of fossil, and potentially different between different layers, and there shouldn't be, depending on the individual fossil, there shouldn't be an overall blanket coverage of the same or of completely random crystallographic orientations. But more on that hopefully next year. So, just as a recap of this preservation protocol, if we can get from these things to saying they're well preserved, is that on still or is that gone? Okay. If we can say that these things are well preserved, we can use them for oxygen isotope analysis, and we need a robust protocol to do that. So, microstructures, we do have at least crudely well preserved microstructures. And the ultrastructure scale, it seems like we do have well-preserved ultrastructures, and again, this is ongoing work, preliminary work here. Chemistry is in spots, excellent in some places, avoiding fractures and picking samples and sample sites carefully. Again, chemistry can be shown to be well-preserved in these specimens. And crystallography is ongoing work. But at the moment it looks like we're getting towards some specimens, or some parts of specimens at least, that do have well-preserved, that are well enough preserved to investigate for this oxygen isotope proxy, which would hopefully, and in the fullness of time, fill in the 50 million year gap that currently exists at the base of the Phanerozoic and start to give some quantitative context to the Cambrian explosion. Thank you for listening. Take any questions.